Throughout this course, we went over different methods in order to prepare aldehydes and ketones. This is a revision of the methods that we explained in Organic 1 and Organic 2. So this is chapter 9 in Organic 1. You can do ozonolysis of the alkene, break the alkene with a mild oxidizing agent. When ozone is coupled with zinc, in presence of water or dimethyl sulfide, that is going to make the ozone a mild oxidizing agent. So if there's any hydrogen on the alkene, then this hydrogen is going to stay. It's not going to be oxidized further, so you're going to end up getting an aldehyde and a ketone. All what you're doing is you're breaking the double bond in half of the alkene and introducing an oxygen to each end of the double bond, so you're getting an aldehyde and a ketone in this case. Now, if you're using a strong oxidizing agent, then this hydrogen will get oxidized further into a carboxylic acid. Ketones will not be oxidized further. Ketones will stay ketones because they do not have a hydrogen on the carbonyl. This is an example over there. So as long as you have hydrogens and you're using a mild oxidizing agent, the hydrogens will stay in the form of aldehyde, and this is how you get aldehydes and ketones. Another way to prepare aldehydes and ketones is to start from alcohol and do oxidation. Oxidation is the loss of two sigma bonds, so you lose two hydrogens and you gain a pi bond, which is a carbonyl. Depending on the strength of the oxidizing agent, you can either get the aldehyde ketone or you can get the carboxylic acid. So if your oxidizing agent is very strong, we've listed those in earlier chapters. So sodium dichromate, potassium permanganate, all of those, they work with acids. Or we can use Jones reagent, which is H2CrO3. This is a chromic acid. This is a very strong oxidizing agent. It will oxidize the primary alcohol all the way into a carboxylic acid. It will pass by an intermediate, and the intermediate is going to be an aldehyde, but that intermediate will not be isolated, so the hydrogen over here will be oxidized further due to the strength of the oxidizing agent into an OH. So you're going to get a carboxylic acid, and this is just from primary alcohols, not secondary alcohols. Now, if you wish to isolate the aldehyde, you can use a milder oxidizing agents than those strong ones. The mild one is the PCC. So we use that, and we're going to isolate the aldehyde. It stays as is. For secondary alcohols, it really doesn't matter what type of reagent that you start with, strong or mild, it doesn't matter. You're breaking the two sigma bonds and you're forming a pi bond, so you're always going to get a ketone as a product. Tertiary alcohols have no oxidation. The reason why, because when you do oxidation, you need a hydrogen on the carbon that carries the OH. After all, you are losing two hydrogens and you are making a double bond. If you have no hydrogen on this carbon, then the reaction cannot proceed and you will have no reaction. Another method to get aldehydes and ketones is simply by Friedel-Crafts acylation. This is in chapter 15. So you make your acyl group, your electrophile, and that electrophile is going to attack or react with the benzene by a two-step mechanism to restore the aromaticity of the benzene. Now, once you get the ketone in there, we know that the ketone on the benzene, this is an electron withdrawing a group. Change this group into an electron donating group. All what you need to do is just reduce the carbonyl into a CH2. So we call it reduction. Again, this is a form of a reduction because we are getting rid of oxygen and we are introducing a hydrogen. So every reaction that you are doing and you are adding hydrogens, taking away oxygens, this is called a reduction reaction. In this reaction, there are two reagents that we've talked about. We've talked about the Clemmensen reduction reaction, and we've talked about the Wolff-Kishner reaction. The clemensine is the zinc in presence of HCl. This is wrapped in mercury, and the Wolff-Kishner is using the hydrazine in presence of a base. Another method to form aldehydes and ketones is by adding water to the triple bond. The reaction is called hydrolysis. And hydrolysis can happen to triple bonds either with terminal triple bonds or with internal ones. When you want to hydrate a terminal alkyne, already this hydrogen is acidic. So you cannot go ahead and add an acid like that in the first step. So what you need to do is add HgSO4 in there, and the HgSO4 will serve as a catalyst to start the reaction. This we use it every time we have a terminal alkyne so that we can start the reaction. You're going to form the cyclic mercurinium ion, and then water is going to attack. This is the difference between terminal alkyne and internal alkyne. Please review the mechanism for this reaction. You already have the notes. And this is a chapter 9 from Organic 1. So here what you're adding is water according to Markovnikov. Hydrogen will add to the less substituted carbon. OH will add to the most substituted carbon. So hydrogen will add here and the OH will add there. The addition breaks only one pi bond. So you're going to end up having the other pi bond in there, and you're going to end up getting the enol form. Enols are unstable, and the reason why they are unstable because they have a double bond that is directly attached to the OH. The double bond is electron rich and the oxygen is electron rich, so you have two nucleophiles that are next to each other. The structure does tautomerization. The structure rearranges to form the most stable product in there. And the rearrangement is called tautomerization. The way that you rearrange is the following. You take the double bond and you move it to the carbon-oxygen bond so that you can form a carbonyl in there. And you take the hydrogen that is on the oxygen and you move it to the adjacent carbon. And this is how you get a ketone. Always ketones, they are more stable than their enol form. And the process to go from the enol to the ketone is called a tautomerization. If you have an internal alkyne, you don't have any acidic hydrogen over here, so no need for you to use HgSO4. You can directly do the hydration in there, and the hydration will proceed by Markovnikov again. Hydrogen will add to the less substituted carbon. This carbon is the less substituted side because you have one carbon over here versus two carbons over there. And then the other carbon of the triple bond will have the OH. You're still going to be stuck with the alkene, so this is an enol. You do the tautomerization, move the double bond, take the hydrogen, move it to the adjacent carbon, and you're going to get your ketone. Always show your carbonyls as your products. Do not show the enol as the final product. This is not stable. We can also do hydration by anti-Markovnikov. We are still in chapter 9 here, but the product now is going to be an aldehyde after the tautomerization. This is an anti-Markovnikov reaction. So hydrogen will add to the most substituted carbon. Hydrogen will add here, and the OH will add there. We're still going to get the enol, and you're going to still do the tautomerization, and you're going to get the aldehyde in this case only for terminal alkynes. For internal ones, you are going to get the ketone.